Degenerate games. The uniqueness of an LH path requires a non-degenerate game. In a degenerate game, a vertex of P, for example, may have more than m labels. When that vertex is represented as a basic feasible solution as in 3.17, this means that not only the m non-basic variables are zero but also at least one basic variable. Such a degenerate basic feasible solution results from a pivoting step where the living variable representing the label that is picked up is not unique. As an example, consider the 3 by 2 game. A equals to 332506, B equals to 332631, which agrees with 3.3 except that B12 equals to 3. The polytope Q for this game is the same as before, shown on the right in figure 3.2. The polytope P is the convex hull of the regional vertices 0, A, C, D, E, shown on the left in figure 3.2. So vertex B has merged with A. The new facets of P with labels 4 and 5 are triangles with vertices ADE and ACD, respectively. In this example 3.18, the first step of the LH path for missing label 1 would be from 0, 0 to A0, where the two labels 4 and 5 are picked up because vertex A has the 4 labels 2, 3, 4, 5 due to the degeneracy. If then label 4 is dropped in Q, the algorithm finds the equilibrium AS and no problem occurs. However, dropping label 5 in Q would mean a move to AP where label 3 is picked up, and none of the two edges of P that move away from the facet with label 3, which are the edges from A to D and from A to E would, together with P, be one almost completely labeled, so the algorithm fails at this point. Degeneracy can be resolved by perturbing the linear system lexicographically, which is well known from linear programming. Assume that the system B transpose times X plus S equals to 1, say, is changed to the perturbed system B transpose X plus S equals to 1 plus the transpose of epsilon to the 1, epsilon to the 2, epsilon to the n. After any number of pivoting steps, this system has the form C times B transpose times X plus C times S equals to C times the 1 vector plus C times the transpose of epsilon to the 1, epsilon to the 2, and epsilon to the n. For some invertible matrix C, the corresponding perturbed basic feasible solution may have a zero basic variable, which is a row of C1, but for sufficiently small epsilon greater than 0, it is positive if and only if in that row the first non-zero entry of that matrix C is positive. This is the invariant maintained by the algorithm using a more general lexical minima ratio test. No actual perturbance is required and C is already stored in the system as the matrix of coefficients of S as seen from 3.19. Degenerate games may have infinite sets of equilibria. In the example 3.18, vertex A of P, which represents the pure strategy 1, 0, 0 to the transpose of player 1 together with the entire H that joins vertices R and S of Q, defines a component of Nash equilibria where player 2 plays some mixed strategy y4, 1 minus y4 for 2/3, which is less than equals to y4 less than equals to 1. However, this equilibrium component is a convex combination of the extreme equilibria AR and AS. In general, even in a degenerate game, the Nash equilibria can be described in terms of pairs of vertices of P and Q. We write conv U for the convex hull of a set U. Proposition 3.8. Let A be a bimatrix game. and xy is in a P times Q, then xy rescaled is a Nash equilibrium if and only if there is a set U of vertices of P minus the set of zero vector and a set V of vertices of Q minus the set of zero vector, so that X is in convex hole of U and Y is in conv of V, and every UV in capital U times capital V is completely labeled. Proposition 3.8 holds because labels are preserved under convex combinations and because every face of P or Q has the labels of its vertices, which are vertices of the entire polytope. For details, see von Stengel, 2002, Theorem 2.14. The following algorithm, which extends algorithm 3.5, outputs a complete description of all Nash equilibria of a bimatrix game. Define a bipartite graph on the vertices of P minus the set of zero vector and Q minus the set of zero vector, whose addresses are the completely labeled vertex pairs xy, the cliques maximal complete bipartite subgraphs of this graph of the form U times V, then define sets of Nash equilibria conv U times conv V, whose union is the set of all Nash equilibria. These sets are called maximal Nash subsets. They may be non-disjoint if they contain a common point xy. The connected unions of these sets are usually called the topological components of Nash equilibria.